Good morning everyone, and welcome to today's worked exam answer video. I've come back through my squared paper book and found that I did not do this acids and bases question initially, so I thought, why not do it now? Feels like I haven't done an acids and bases question for a while, and this one has quite a few I guess different or trickier aspects to it, so I thought let's have a go. There's also bizarrely in this question, and this is not me, I haven't typed this up, there's a number of typos. So for example, nitric acid, HNO, I don't know what's going on there, but that negative should not be there. So it's just HNO3, and then further down the question we've got centimetres to the -3 for a volume and 50 centimetres to the -3 for a volume, so again they shouldn't be there. So I'll get rid of those now. But it says that nitric acid is a strong acid, and then we've got ethanoic acid in this question, which is acting as a weak acid. So strong acids will fully dissociate into their ions, whereas a weak acid will only partially, or an even better word would be to say slightly, dissociate into its ions. So we don't get anywhere near sort of 100% dissociation with a weak acid. And to start with, we have to show how the ethanoic acid would behave as a weak acid in its reaction with water. So the idea that it will give up protons, but it's not going to be like a full forward facing arrow that I'm going to use, because it's not all of the ethanoic acid that is going to dissociate. So we end up with an equilibrium being formed between the weak acid and its ions. So I would argue there's two ways we could do this. One would be as a normal sort of dissociation equation. So ethanoic acid, reversible arrow, to show that we're going to end up with an equilibrium of CH3CO- plus H plus. Alternatively, because it does say in the reaction with water, even though this will be a solution, we could have it like this: CH3COOH plus water. Again, this is going to generate an equilibrium, so I need my reversible reaction arrow, and it's going to form the same CH3CO- ion. We are going to lose a proton. That proton would be gained by the water to give us H3O plus. So the key thing is here, if it was nitric acid we were thinking about, it would all be turning into NO3 minuses and H pluses. Definitely not with a weak acid. Okay. Then this is quite interesting because we're going to react two acids together. Now, if we react two acids together, we can't have both of them being an acid because they can't both give up protons, because where they're going. So one of them, and it's always the weaker acid, would then be acting as a base, so accepting the proton from the stronger acid. So it's a bit of a weird one to think about perhaps, but in terms of what we're going to write for our equation for this reaction, we're going to need nitric acid, HNO3, plus ethanoic acid. If the nitric acid is acting as the acid, because it's the stronger of the two, then that is going to give up its proton to become NO3 minus, and it therefore has to be the ethanoic acid that is going to gain that H plus, aka act as a base, and that's going to go on the end there, and it will be the oxygen in the Cu group that would have the positive charge. So that does look a bit weird. But hopefully if we understand what we mean by acid and base, we can still have a go at that, even though it's potentially very unfamiliar. Then we're moving on to think about reactions of nitric acid with, well, we're going to dilute it in the first question, and then we're going to react it with an alkali in the second question. So we've got two separate beakers. The first beaker we're going to use in the first calculation, and then essentially we've got a new beaker, same volume, same quantity of our nitric acid, which is 100 centimetres cubed of that concentration, and it's going to be doing slightly different things in each of the two calculations we're going to do. So first of all, it says we've got to calculate the pH of the solution formed after 50 centimetres cubed of distilled water are added to beaker A. So if we're adding water, we are going to change the concentration of the nitric acid, but we're not going to change the moles. So anytime you're doing a dilution kind of question, the first thing we're going to need to do is work out the moles in the original solution, because they will stay the same. Then we can use the new total volume to work out the new concentration, and from there we can get pH. So initial moles of the nitric acid is going to be equal to the volume, which I need to convert into decimeters cubed by dividing by 1,000, and then we're going to times that by concentration, 0.0125. (1.25) times 10 to the minus 3. And then the new total volume, once we've added the water, is going to be the 100 we had originally in the beaker and the extra 50, so we just need to add those together, which is going to give us 150 centimetres cubed, which again I would need to then convert into decimeters cubed. Then we can get the new concentration of the HNO3, and concentration is equal to moles divided by volume. Which is 8.3 recurring times 10 to the minus 3, so 8.33 times 10 to the minus 3 to 3 significant figures, and that's concentration, so mole dm minus 3. And then if we want to calculate the pH, we're always going to need the H plus concentration. Now because nitric acid is a strong acid, all of the HNO3 will dissociate into H plus and NO3 minus ions, and therefore the concentration of the HNO3 is equal to the concentration of the H plus ions. So that's going to be equal to 8.33 times 10 to the minus 3 mole dm minus 3. And then anytime we want to work out a pH, pH is worked out by doing minus log to the base 10 of your H plus concentration. So pH of this solution is going to be minus log answer. pH should always be given to 2 decimal places. It does say it in the question, but even if it doesn't, should be always to 2 decimal places. 2.08. Ta-da! So got to work out moles in the original solution to get the new concentration when we've worked out what the new volume is, and then because this is a strong monoprotic acid, the concentration of the HNO3 and the concentration of the H plus are the same, and then we can use our standard pH is equal to minus log base 10 of our H plus concentration. Okay. And then the next calculation, we're using beaker B, so it's the same volume and concentration of nitric acid, and therefore we already know the moles of that. Now we are adding an alkali, so calculate the pH of the solution formed after 50 centimeters cubed of that concentration of sodium hydroxide, which is an alkali, are added to beaker B. So we're going to be doing neutralization. Whether we neutralize all of the acid or all of the alkali is what we're going to have to work out, and in order to do that we're going to need a balanced chemical equation for the reaction so that we can then have a think about which of those two substances is in excess. So HNO3 reacting with, and I'm just going to give myself some room to do the maths underneath, sodium, is sodium? Yeah, sodium hydroxide. So an acid plus an alkali makes a salt, NaNO3 plus water. And I'm not interested in the products as such in this case, but I need to check that it's a 1-to-1 ratio, so I have to write the whole thing to make sure it's balanced, which it is. Then I'm going to do like an initial moles row, and we already know the moles of the HNO3 within the beaker as 1.25 times 10 to the minus 3. And then for the sodium hydroxide, we can figure that out from the volume and concentration that we've got in the question. So just want to check I do that right. 0.05 decimeters cubed times 0.0108 gives me the moles. So 5.4 times 10 to the minus 4. And then because it's a 1-to-1 ratio between the acid and the alkali, we can see that we've got more nitric acid than we have sodium hydroxide. So all of the sodium hydroxide is going to react away. A lot of the nitric acid is also going to react away, but there will be some moles of it left. Now in other questions it might be that the alkali is left over, or there's an excess of that rather. And all that will change is whether you go on to do a strong acid calculation or a strong alkali calculation. And you do that the normal way that you would any strong acid calculation or any strong alkali calculation. So for the alkali one, you'd have to use your Kw expression rearranged, whereas because we've got an excess of the nitric acid, we're going to be able to work out the new concentration of the nitric acid. That will immediately give us the H plus concentration, and then we can do the same. So my next row is going to be kind of like the reacting moles or your changing moles. So we're going to lose all of the alkali. There's going to be none of that left. And we're going to lose the same because of the ratio. 5.40 times 10 to the minus 4 moles of the nitric acid. And then that is going to give us how many moles of each thing are left, which for the alkali is none. I can do that math. And for the nitric acid, $7.1 times 10 to the minus 4. So that is how many moles of nitric acid we now have in the beaker. There's no alkali in there anymore. We don't need to worry about the formation of products because this was not a weak acid, so we're not in buffer territory here. It's just neutralization. What have we actually managed to neutralize? What's left over? Okay, I've got the moles of this. So now what I need to do is get the new concentration. And why do we need to get a new concentration? Because we now have a new number of moles firstly, but we also have a new total volume because we have added the 50 centimeters cubed of the sodium hydroxide into the 100 centimeters cubed that was already in the beaker. So we now have again a new volume of 0.150 decimeters cubed. So the new concentration will be the moles. So 7.10 times 10 to the minus 4 divided by, again, 0.150 decimeters cubed, because that is our new volume in the beaker. Which is 4.73333, so 4.73 times 10 to the minus 3 mole per decimeter cubed to 3 significant figures. And then, as I wrote before, because it's a strong acid, it's all going to dissociate into its ions, so the concentration of the nitric acid is going to be the same as the concentration of the H+. So to save myself a little bit of time, I'm just going to write that the H+ concentration is also equal to 4.73 times 10 to the minus 3 mole dm-3. And again, pH is going to be worked out by doing minus log base 10 of that concentration. So it's not going to have a very acidic pH, but that's expected because we don't have a lot of moles, we don't have a great concentration of H+ ions, so yeah, it's going to have a less acidic pH than the question above. 2.32. And that's the end of our question. So I hope that everything I've explained there makes sense, but as always guys, if you have queries that you want to check out with me, please do. On the video, drop me a message, email me, whatever you would like to do. Any requests, again, as I've said before, just again, get in touch. And if not, then I will keep producing what I think are helpful videos until I hear otherwise. And I'm sure that I will be back with a new video soon. Take care of yourself guys, and thank you so much for watching.